Hello, this is the second lecture of CS147 Computer Architecture Study in San Jose State University. These lecture topics list are quite long. We'll discuss clock system model, memory system model, control unit model, von Neumann architecture, and we'll touch on the system softwares. So this clock system model, as we discussed in the previous lecture, lecture 1, we discussed about this ALU or arithmetic logic unit, and it looks like schematic diagrams looks like this, and the functionality of this specific piece of hardware is that we give this hardware two operands, like 32-bit binary numbers, binary value, and operation code encoded with a 6-bit, and this produce result in terms of 32-bit result value. Like let's say we want to add like 10 and 5, we pass 10 and 5 value to this ALU and pass addition encoded bit pattern for the addition, and then the result it will produce like 15, like 10 plus 5, 15. Now the point is that this result will not be produced instantaneously. There would be some delay, however small that delay may be. Even from a human perspective, probably we won't feel anything, and to us it will appear to be very instantaneous result. But there is certain delay involved in the nanosecond range. So you know that 1 nanosecond is 10 to the power minus 9 seconds, which is not really, that delay is not within human perceivable range. It is really fast for us to understand that transition or to even understand the delay, but that delay will be there. Okay, so result is not instantaneous, and this delay can be represented in a timing diagram. Okay, so for most of you, this timing diagram is pretty new concept. So let me explain a little bit on this, what the timing diagram is and what it looks like. So each time is represented in a vertical line, like TA or T1, TA, T2. For example, these are some discrete time point. You can say like is a 6 o'clock, 6:01 and 6:02. These are the time. But this is really, we are representing in probably microsecond or even nanosecond range this time. So it's not really 6 o'clock, 6:01, 6:02 in that sense, but it is time step in the microsecond or nanosecond range. And at this point, at each of these discrete time point, we represented how a signal changes. Okay. So for example, this operand 1 is a multi-bit value, like it has 32 bits. So we represent these things in a trapezoid way to represent this is not a one single signal, but it is a group of signals. They are transitioning together and making some value changes. So same for operand 1, operand 2, and operation code, because they all are multi-bit, and also result is multi-bit, right? So it is saying that they are changing at some time point. So it is, this diagram is really telling you that at time point T1, operand 1, operand 2, and operation has changed the value from whatever previous value there were, and then the last the downmost this bunch of signal represents for the result for the, let's say it is a ALU revision 1.0, okay, some revision of ALU 1.0. So this was there was some values previously from the previous operation, and after this operand and operation are presented to the ALU, this result is computed and reflected at a time point TA. Okay. Whereas at T2 time, what happens? Those operands and operation are changed to the next set of operand and operation code. Okay. So T1 we start the operation, or we establish or set or send, whatever you want to say, about this operation. We send those operation and operand to the ALU, and then after some time like let's say delay amount of dA, that is T1 plus dA, that time, which is like time point TA time point, at that time point ALU evaluates this operation and present the result to us. So that is the delay. Okay, so these vertical lines are time line. Okay, and we represent the changes of the multi-bit signal like buses. We call it bunch of signals as bus. So this 32-bit value changes are represented in this fashion in a timing diagram. So by looking at this timing diagram, what all we can say is that when we present some operation and operands to the ALU takes dA amount of time to compute them and present the result at certain time after some time point of T1, and we can compute TA equals T1 plus delay A or dA. Okay, and at the T2 we take down and change to the next value. Now, depending on the ALU implementation and underlying technology used, this operation delay can vary from one implementation to another. Okay, even same ALU, if you operating under certain physical condition, for example, if it is it is operating in the higher temperature region or high humid region, that also affect the electronic system to vary the delay, this amount of delay before the result appears. Okay, so means like either we change the design, make a faster ALU, or go to a new technology which compute faster. That's one scenario. Another scenario that's even if the same ALU, same technology, same design, if you operate in a very cold condition versus if you operate in a very hot condition, this delay varies from each other. Okay, so this is a very tricky problem to handle, because this amount of delay, how it changes, we never know, because your operating condition changes per like every moment, basically can change. So your next revision of ALU, let's take out this variation due to the weather condition, but let's say we have enhanced the ALU to make an revision 2.0, which takes less amount of time like dB, and it computes the result faster now. Okay, so D and dB are the operation delay, and dA here has a more delay than a revision 2, which is dB. Okay, so your result start coming faster from this next revision of ALU. Now the point is that ALU itself is not making the whole computer, right? So other components needs to interact with this ALU, and means other electronic component, right? If there is no human factor inside the computing system which controls and kind of adjusts when to pick up the result, when not to pick up the result, by looking at when the result is available or not. So this is all electronic system, and they need to rely on something to tell them when I should take the result, when my result is done. Okay, they cannot just assume that always take a dA amount of time or dB amount of time, because one of the factor is that it can be operated under different weather condition, and this delay will vary. So it will get, all operation get messed up, right? So rest of the computing system is trying to use the result of the ALU from the ALU, right? So rest of the computing system is requesting ALU to perform some mathematical operation, and this result is being consumed. So question becomes, when this result should be consumed. Now to solve this problem of variable delay, okay, clock is introduced as a provider for a common synchronization point or common reference point. So clock, what it kind of tells that in terms of previous picture, it can tell something like this. Okay, I give you the operation T1 and I am guaranteed to get a result at T2 point. Let's say we fix that number. Internal delays can vary. It can come fast, it can come slow, etc., etc. But what we can claim from the system perspective that, hey, I'm giving you some data or information to crunch at the time T1 and I'll get back the result at T2. You better make sure that you compute result within that delay. All right, and that T1 and T2, this reference time to both ALU and the rest of the computing system, is given by the clock. Okay, so it is an agreement between subsystem that requires the operation is concluded within a predefined number of clock ticks, time, and etc., etc. But it is kind of an agreement between these two systems, the computing system and ALU, for in this example, that hey, I'm giving you input in this time point and I will expect you to compute by this time point, by this future time point. You can be faster, slower, but give us a guarantee that you will give us result at T2 if I give you input at T1. Okay, now these reference times, right? So to establish a reference time, this clock system must generate an very stable stream of timing reference which can clearly indicate time points. Okay, so the easiest way to do it is to make one signal, let's name it a clock signal. It's changing its value. Like we know the binary value, all computing system goes with the binary value, use the binary values. So if this specific signal can change its value from 0 to 1 and back to 0 and repeat these things under a fixed time period, then we establish a fixed reference time point. Then we can tell that, hey, if I sending an input to this clock, okay, this time point, I expect to get a result back, let's say 10 or 20 ticks after. Okay, so it whatever that ticks and that time is, right? So these ticks, okay, means like when we are transitioning from 0 to 1 and then back to 0, okay, that's whole one cycle. So we are 0, staying 0 for certain time, then went up to logic 1 and then come back to 0. This whole time is called a time period, okay, and that transition from 0 to 1 or 1 to 0 is, we can say, it's one tick, let's say. Okay, so in a very rough terminology. So these clock ticks are really fast. Modern laptop offers more than like 2 gigahertz CPU speed, which means it is kind of ticks are 0.5 nanosecond apart. 2 gigahertz CPU speed is 0.5 nanosecond apart, this each tick, like one transition from 0 to 1 and then next transition from 1 to 0, they are 0.5 nanosecond apart, and where 1 nanosecond is 10 to the power minus 9 seconds. So you can imagine that's really fast change of values, and this change happens forever, right, till your computing system is up. So here some more details on the clock system. So as I said, clock is represented as a continuous flipping between logic 0 and logic 1, which is kind of swing between the ground and VDD. Like this is electrical signal, right? So you know that 0 is represented by like no voltage value on that specific wire, and 1 is represented as a full like whatever the operating voltage, 1 volt or 1.2 volt or 0.8 volt, on that represent a logic 1 in a certain electrical wiring. So this is a continuous, a clock signal. If you look at that wire, then you will see it's continuously flipping from 0 to 1, back to 0, then 1, 0, with a fixed time period. So there is a precise time period. It's not randomly happening, like wait for some times, randomly it goes to up and then randomly goes to, it's not. It's very predefined, precise stream of 0 and logic 1, and your clock is like going up and down, up and down. Often we represent with a square timing diagram, which is like basically you don't see a trapezoid. If you just make in a perpendicular line, that becomes a square signal. We often use that. I have shown you all these as a trapezoid signal to capture more realistic clock signal, how it look like. Okay, but it is again very clean. Like in reality, it is not even this clean. But point is here, from logic 0, electrical signal will take some time to go up to logic 1, and then it will definitely take some time to go down from logic 1 to logic 0. Okay, so so if we look at the 50% point of the trapezoid rising edge or falling edge, this is a rising edge 0 to 1, falling edge 1 to 0. If you look at them, the 50% point, this if you measure this time distance, that's your high time. Okay, time at which this is kind of logic high. So reality, in reality the logic high is, strictly speaking, is this part. Okay, logic high is this part. If we want to measure it very strict, when it is absolutely in logic 1, because this is kind of in the transition between 0 and 1, so this is really not, strictly speaking, it's a logic 1. But from calculation point of view, your T high is measured from the 50% point of these trapezoid signals. Okay, similarly, T low, or time during which the signal remains low, is measured from 50% of the falling transition to the 50% of the next rising transition time. Okay, so this is your transition high, transition low time. Okay, and then if you add up TH and TL, that's your time period. Okay, that's your time period. So time period is basically your 50% of your first rising transition to the time of the 50% time point of the second rising transition. That's the time period. And also falling is, if you want to like look it from the fall transition perspective, so 50% of the first falling transition to the 50% of the next falling transition is your time period. Now the beauty of this clock signal is, and all clock subsystem guarantees, that wherever you measure this time period, from this point to this point, or this point to this point, or this point to this point, you will get the same number. So your time period is very fixed. Not only that, your time T high and T low, they are also fixed. Okay, so how do we calculate the time period from given like frequency, which we often see when we kind of decide to buy a laptop? We see the clock speed, it is 2 gigahertz, 1.2 gigahertz, 1 gigahertz, something like that. So it is like the physics formula, 1 by f, means T equals 1 by f is the formula to compute your time period of the given clock. So that means if you are given a time period, like let's say time period is 1 nanosecond, for example, you can compute corresponding frequency of the clock is 1 by t. Okay, so it's T equals 1 by f. This is purely a physics formula of how you compute frequency. Of course, then the unit follows the same physics physics unit is hertz. Okay, gigahertz is just an unit extension of the hertz, and hertz definition from the physics 101 is 1 cycle per second. That's the meaning of the hertz. So if I say if it is a 1 gigahertz, mean it is 10 to the power 9 cycle per second. Okay, so the time period will become 1 by 10 to the power 9 per second. Okay, 10 to the power 9 per second, which is becomes like 10 to the power minus 9 1 by second, right? 1 by second. So and that's become your we're calculating the time period here. So 1 gigahertz is 10 to the power 9 cycles per second. That means your time period is 1 by f, which is like in this case 1 by 10 to the power 9 cycle per second, which becomes 10 to the power minus 9 second, right? 10 to the power minus 9 second, and which becomes your 1 nanosecond basically in terms of unit. So that's how you compute time period of a given clock from a frequency and vice versa. And if it is a trapezoid signal, your high time, low time can be given, or it can be, or some other information can be given, just like some arithmetic problem, and you can be asked to compute the high time, low time, or maybe like how much time it is really in the high logic region, which is basically this computation of this part or computation of that part, just saying that. And there is another important aspect that is called a duty cycle, which is also characteristics of a clock system, which tells me how much time it's spending itself in the high state, which is, if you see from formula perspective, your duty cycle is really time high, th, by your time period multiplied by 100. So it is kind of an percent. So if I say my duty cycle is, let's say, 45%, right? Duty cycle is 45%, and I know, let's say, t high is 0.45 nanosecond. Then what is my time period? We can calculate from this formula. So we have given this whole number and this unknown factor. This is a known factor, t high, which is 4.45 nanosecond, for example, and multiplied by 100 by t equals that whatever that duty ratio 45% we have given. So you solve the equation, you get the time period. Okay, so keep these formulas in mind. Okay, how do you compute period from given frequency? What is the definition of a duty cycle? What is the concept behind t high and t low timing? How it measured in a real trapezoid clock signal? And those are pretty much your kind of clock related formulas, and maybe some numeric problem can come in your exam and stuff like that. So please pay attention to those part. And the other part, important part here, is these arrows. Like sometimes it is given in the diagram, sometimes it is kind of implicit, and people doesn't want to do it because it may give the timing diagram some cluttering effect, like too many arrows going on here, right? But if it is present, what does it mean is this, that these changes is related to this time point. Means when the clock goes and crosses the midpoint, that triggered the changes in operand 1, operand 2, and operation code. So you see, these are all related clock edges. Okay, and also this one triggered your ALU changes as well. That's what this means, right? And so this is all triggering, like when I triggered and with respect to this time point when my real operation is completed. It is kind of clock edge relation. And then the other part here in this diagram is showing that when I am sampling the result, sampling the some output, okay, when I'm sampling the output. So it is always saying that I change my operands at this point and I'm going to sample the result at this point, so that your ALU, whoever is designing, implementing the ALU, better make sure the result comes before this time, because this time is a fixed time, and this is, we're talking about 1 clock period. It may be like 2 clock period, it may take 3 clock period, but point is that it's a fixed, previously specified time, and this is a handshake between your rest of the subsystem and the ALU in this example and in this discussion. So this is an agreement that, hey, I am giving you input at this time point and I'll sample your output at this time point, which is a fixed time for the entire system. Your design ALU better produce result by then. It can come faster, it can come slower. Rest of the system doesn't really care. It basically picks up the result always at this time point. Okay, so that's about the clock systems.